Welcome back to the deep dive. Today we are taking a trip into, well, really the highest stakes possible, structural integrity within a nuclear power plant.
Yeah, totally.
If you want to know how the people responsible for safety sleep at night, it's because of the kind of engineering assessments we're about to explore. We're diving deep into how engineers guarantee that vital piping components, specifically those made of high toughness stainless steels like SA312 Type 304 LN, won't catastrophically fail, even if they already have a crack or some kind of defect present.
It really is the ultimate stress test. I mean, when you're talking about primary coolant pipes, these are systems that just cannot fail under any circumstances. So our mission today is to understand the standardized tool used for this assessment, the failure assessment diagram, or FAD.
FAD.
This approach provides a rigorous, nonlinear shortcut, essentially. Right. It's a way to take a known flaw, usually near a welded area, which tends to be less ductile.
A weak link.
Exactly, the weak link, and determine mathematically if it's acceptable under the actual operational load or if it truly means, potential failure is imminent.
And the core relevance for you, the listener, is pretty straightforward. This FAD analysis dictates the safety margin. It tells engineers, yes, you can operate this, or potentially no, shut it down immediately. We're focusing on the welds because, as you said, those are the areas where the original stainless steel meets a filler material. That makes them the structural weak point, the spot where lower ductility makes a fracture more likely.
Precisely.
Okay, let's unpack the FAD itself then. It sounds extremely technical, maybe a bit intimidating.
It can seem that way.
But at its heart, it sounds like it's a beautifully simple, sort of two-dimensional safety map.
That's a great way to put it. A structure fails fundamentally in one of two ways. Either it kind of bends and collapses plastically.
Plastic collapse.
Right. Or it just snaps suddenly, brittle fracture. The FAD is designed to combine the assessment of both those failure modes. Oh. That's absolutely right. So the FAD plot itself defines an acceptable region of safety, and that region is bounded by something called the failure assessment line, or FAL.
FAL, got it.
To use it, we have to calculate a single assessment point based on the specific conditions of that pipe, the load it's under, the size of the crack, and the material's inherent properties. And this assessment point, it has two crucial coordinates, LR and KR.
LR and KR. Okay, let's go through those ratios one by one because they really are the foundation of this entire deep dive. Tell us about LR, the load ratio. How do we interpret that number?
Okay, LR is all about capacity utilization.
Yeah.
You can kind of think of it as how much of a bridge's total allowed weight limit you are currently using.
Okay.
It tells you exactly how close the component is to plastic collapse, that point where the material completely yields and deforms permanently. Mathematically, it's simply the ratio of the applied bending moment to the limit load moment, which is the material's absolute theoretical capacity before it buckles or yields excessively.
So if your LR is, say, a 0.5, you're using half the plastic capacity. And if it hits 1.0, you are theoretically right at the point of collapse, regardless of any crack.
Precisely. A higher LR means you are closer to that plastic failure point.
Mm-hmm.
Now, for the other axis, KR.
Okay.
Well, this is the fracture ratio and measures the component's resistance to fracture.
Okay, so if I picture LR as the maximum strength test, maybe KR is more like the sharp object test, how resistant is it to that crack growing?
That's a great analogy, actually. KR is the ratio of the applied stress intensity factor. That's the SA, the actual measure of the stress concentrating right at the crack tip, to the material's inherent fracture toughness.
Fracture toughness
is
like its ability to absorb energy.
Exactly. Its ability to absorb energy before that crack begins to spread uncontrollably, possibly very rapidly. So a high KR means the stress at the crack tip is getting dangerously close to what the material can handle.
Okay, so the verdict seems simple then. You calculate your specific assessment point, that LR, KR coordinate pair. If that point lies inside the failure assessment line on the diagram, the flaw is acceptable. The crack is considered stable under that load.
Correct.
But if it lands above or outside that line, the structure is predicted to fail. Instantly, potentially.
That's the prediction, yes. Unstable.
And landing exactly on the line.
That means you are at the critical condition, essentially zero safety margin left. It's the boundary.
Right on the edge.
And that's the beauty of FAD. It provides this visual and quantitative safety check that cleverly accounts for both ways the pipe could fail. It doesn't let you assume that just because the pipe material is tough, it can handle any load near a crack, and it doesn't let you assume that because the load is low, a crack is irrelevant. It forces you to consider both.
Okay, this is where we move past the theory and into the actual experimentation that engineers rely on. Because theory is one thing, but
real pipes are another.
Exactly. The study we're looking at focused on real-world welded pipe specimens. They used 3 specific pipes of that high-toughness SA312 Type 304 LN steel. And crucially, each one had a large, manufactured, circumferential through-wall notch, a simulated, pretty serious crack placed right in the weld zone.
Right. They weren't testing pristine, perfect pipe. They were deliberately testing damaged pipe to see where the limits really were.
Makes sense.
And the specs, they really emphasize the real-world scale of this testing. The nominal outer diameters of these pipes varied significantly, from about 168 millimeters up to a massive 325 millimeters.
Wow, okay. Big difference.
Yeah, ensuring the results weren't just specific to one pipe size.
Yeah.
And the artificial notch lengths were substantial too, going up to 170 millimeters. That's a very large flaw to assess.
And the weld itself, you mentioned that's the weakest point. What was used there?
It used a nickel-based alloy, specifically Inconel 82, as the filler material.
Inconel 82, okay.
And it's the material properties of this weld material, not the original stainless steel pipe, that really define the safety floor in that critical region.
That makes sense. You assess the weakest link.
Exactly. So the researchers carefully measured the Inconel 82 weld material properties. It exhibited a pretty strong yield strength, 386.6 megapascals, and an ultimate tensile strength of 666 megapascals. But the critical measure for fracture was its initiation fracture toughness, JIC, which they determined to be 266 kilojoules per square meter.
266 kilojoules. That good, bad, average.
For a high toughness material like this, intended for these applications, it's a respectable toughness. It gives the engineers, a fighting chance against crack growth. It's not brittle.
Okay. Now, there was a key procedural note that simplifies the math, which maybe we should touch on. All these pipes were subjected to post-weld heat treatment, PWHT. Why did they do that?
Yes. They did that specifically to remove residual stresses.
Stresses left over from the welding itself.
Exactly. Welding introduces significant internal stresses. In real-world operation, those residual stresses are a huge factor and add complexity to the assessment. But by removing them through PWHT in the lab, the assessment could focus purely on the effect of the applied load and the material defect itself. It simplifies the model to isolate the core variables we're interested in.
So it creates a cleaner experimental environment to determine the fundamental capacity of the pipe with that specific flaw.
Precisely. Get the baseline right first.
Okay, so we have the pipe, we have the crack, we have the material properties measured, PWHT done. Now we hit what seems like the main challenge of this deep dive. The calculation itself. To find those LR and KR assessment points, the researchers had to choose which established analytical expressions to use. And this is where, maybe, we enter a bit of a gray area.
It can feel like that.
Wait a minute. This is a high-stakes nuclear component. Why do we have competing formulas that produce different safety ratios? Shouldn't there just be one mandated, ultra-conservative standard everyone uses?
That is the essential question, and it comes up all the time in engineering practice. The formulas differ because they operate on slightly different assumptions about how materials behave under load, specifically regarding their capacity to absorb strain and deform before failing. This is exactly why they compared methodologies to see how sensitive the final safety verdict actually is to our choice of mathematical model.
Okay, so let's dig into that comparison. First, the limit load moment calculation, which determines LR, our capacity utilization ratio. They compared Zahoor's expression against Takahashi's expression. This is where a core conflict lies, right?
Absolutely. The difference really boils down to how they define the material's effective strength under large deformation. Zahoor's expression incorporates the flow stress. Now, we need to be clear about what flow stress means. It's typically taken as the average of the material's yield stress and its ultimate tensile stress.
Okay, so yield stress is the point where the metal first permanently stretches, like takes a set. And ultimate tensile stress is the absolute maximum stress it can handle before it starts to neck down and eventually break.
That's right. So flow stress effectively gives the material credit for its strain hardening capacity. It acknowledges that even after the metal starts to yield and permanently stretch, it actually gets stronger and tougher for a while before it fails.
Ah, okay.
Because Zahoor's method uses this higher flow stress value, it consistently resulted in higher predicted limit load moment values. It predicts a greater load carrying capacity for the pipe before collapse. For example, for one specimen, SSPW 625, the LROR calculated using Zahoor was 0.494.
0.494. That seems reasonable, maybe. If the material is tough and strain hardens, you should give it credit for that toughness, shouldn't you?
That's one argument. But Takahashi's expression takes a more conservative approach. It's based only on the yield stress. the very first point where permanent deformation begins.
So it ignores any strain hardening benefit.
Correct. It essentially assumes failure occurs much closer to the initial yield point. This immediately led to lower predicted limit load moment values because it predicts failure capacity was reached earlier. And for that exact same specimen, SPW625, the LR jumped up significantly to 0.672 using Takahashi's formula.
Well, wait, hang on. Let me stop you there. We went from a load ratio of 0.49 to 0.67 just by changing the definition of strength in the formula.
That's correct.
That's nearly a 40% jump in the calculated utilization ratio. That feels like the difference between operating comfortably and, red flagging the component for immediate attention. That's a huge swing in perceived safety margin.
It is a massive swing, yeah. And it absolutely confirms that the engineer's choice of model here is a critical safety decision. It's not just plugging numbers into any formula.
Clearly not. Okay, so that's the LR side. Now let's look at the other axis, determining KR, the fracture resistance. Here, they compared using the material's basic initiation fracture toughness.
Right, the JI value we mentioned.
Versus calculating something called the J integral via load-CMOD method. What's the difference there?
Initiation fracture toughness, JINTA, sounds like what it is, a baseline material property, often measured in a standard lab test. It represents the point where the crack starts to grow stably.
Okay, a single value from a test.
Pretty much. The J integral via the load-CMOD method, however, is derived from the actual test on the pipe specimen itself. It explicitly accounts for the large plastic deformation that occurs around the crack tip as the pipe is loaded. COD stands for crack mouth opening displacement, which they measure during the test.
So if the pipe material is really ductile and it stretches and deforms a lot, absorbing energy before the crack actually spreads significantly, the load-CMOD method captures that whole energy absorption process.
Exactly. It's measuring the total energy being absorbed by the component as it deforms plastically near the crack. Because it includes that plastic energy contribution, it tended to yield slightly higher effective J integral values. This suggested slightly higher actual fracture resistance in the component test compared to just the baseline material property.
Which means the calculated KR ratio would be slightly lower.
Correct. For that same specimen, SPW625, KR was 0.619. Using the baseline initiation toughness, but it dropped slightly to 0.588 when calculated using the load-CMOD J integral. Less dramatic than the LR change, but still a difference.
Okay, so let me see if I have this right. On both the strength side, LR, and the fracture side, KRR, the researchers had a choice. They could use a potentially more conservative calculation like Takahashi for LR and the basic initiation toughness for KR. Or they could use methods that gave the tough material more credit for its actual behavior under load, like Zahoor for LR and the load-CMOD J integral for KR.
That's the core comparison, yes. They then plotted all these calculated assessment points, LR, KR, against standardized safety lines, the failure assessment lines, the FAL. They specifically used lines based on the SINTAP procedure and also the BS7910 standard.
Are those lines very different?
The results showed the failure assessment lines from these different standards actually yielded quite similar boundaries in this case. But it's important to note that BS7910 offers different levels, and Level 2B provides a material-specific line derived from the material stress strain curve, which is generally considered the most precise way to define that safety boundary.
Okay, so they calculated the points using different methods, plotted them against standard, well-accepted safety lines. What was the bottom line? What did they find?
Well, when all the assessment points were plotted on the FAD using, every combination of standardized lines and input formulas, the overwhelming headline finding was positive. In all assessments, all three pipe specimens, even with those massive simulated cracks, were found to be in the stable region.
Okay, so safety achieved across the board. The FAD worked, the pipes were safe.
That is the ultimate conclusion, yes. The components were assessed as stable. However, and this is important.
There's always a however.
There often is. We have to emphasize the nuance we uncovered earlier with the LR calculation. When they used the more conservative Takahashi's formula for the load ratio, remember, that's the method based only on yield stress, which produced the higher LR values.
Right, the one that gave LR 0.67 instead of 0.49.
Exactly. When they used that formula, 2 of the 3 specimens ended up skirting the very edge of that stable region on the FAD plot.
So they weren't technically unstable, but they had effectively zero margin left. They were right on the line, or just barely inside it.
Correct. They were specifically described in the analysis as being marginally below the failure assessment line. This finding really underscores the necessity of choosing the right analytical expression, or at least understanding the implications of that choice. Using a less conservative Zahoor-based method might place the pipe comfortably in the safe zone on the diagram. But using a more conservative Takahashi-based formula forces you to recognize, hold on, this component is actually in a critical condition for this specific notch size and applied load.
So the model choice fundamentally shifts the perceived risk profile.
It absolutely does. It changes how much safety margin you think you have.
Okay, that's a crucial finding. Now, engineers know that input parameters, the measurements they take of geometry, material properties, they're never perfectly precise in the real world. There's always some uncertainty.
Always. Measurement uncertainty is a fact of life.
So did they look into how sensitive the results were to small errors in those inputs?
They did. And that's a crucial step in any robust assessment like this. They performed a sensitivity analysis, focusing on specimen SSPW 625. This basically tells us exactly how reliable our final safety verdict is, even when our initial measurements might be slightly off.
This is great. It's like testing the robustness of the engineering against, slight real-world imperfections or measurement tolerances. What did they vary?
Okay, so they tested varying several key factors. They looked at crack lengths, varying it up or down by 0.5 millimeters.
Tiny change.
Yeah. Pipe thickness up or down by 0.25 millimeters. Again, small variations. Then they looked at the material properties. Flow stress, varying it by plus or minus 25 megapascals, and the initiation fracture toughness, JIC, varying that by plus or minus 25 ampere units.
Okay, so varying both geometry and material strength toughness slightly. What happened?
Well, what's fascinating, and perhaps a bit counterintuitive, is how stable the assessment point was against the geometric variations. Variation in crack lengths and pipe thickness was found to have a negligible effect. The LR and KR values barely moved on the diagram.
Really? So the structure is inherently pretty robust against minor errors in measuring its physical dimensions?
It seems so for these kinds of variations. The assessment wasn't sensitive to those small geometric changes.
But I'm guessing the material properties were a different story.
That's where the sensitivity showed up, yes.
Yeah.
It confirms that it's often the quality control and precise knowledge of the metal itself that dictates the real margins.
Makes sense.
Indeed. They saw significant percentage variations in the LR and KR ratios, linked directly to the inherent variability or measurement uncertainty in those material properties. For instance, flow stress variability, that capacity to strain harden we talked about, caused a maximum variation in the load ratio, LR, of up to 7%.
7% change in LR just from a plausible uncertainty in flow stress.
Okay. And the initiation fracture toughness variability caused an even larger maximum variation in the fracture ratio, KR, of around 10%.
Wow. 10% swing in KR based on potential toughness measurement error. So even though the components remained technically in the stable region in this sensitivity study.
Correct. The final verdict didn't flip to unstable.
A 10% shift towards the failure line means the safety margin we thought we had might be substantially smaller in reality than the baseline calculation suggests.
Exactly. That variability in the measurement or inherent scatter of these critical input properties, while maybe not enough to trigger an outright failure verdict in this specific case, definitely eats into the calculated safety margin established by the FAD. It pushes the assessment point closer to that critical failure line, emphasizing again that material consistency and accurate characterization are the true challenges.
Okay, so let's quickly summarize this deep dive then. The failure assessment diagram, FAD, successfully provided a rigorous two-axis approach to assessing the structural integrity of these critical nuclear pipes. That's the big picture.
Yes, it proved a valid framework.
And while the experiments confirmed the components were fundamentally stable even with large flaws, the choice of calculation methodology, specifically using yield stress versus flow stress for LR via Takahashi versus Zahoor, mattered tremendously. It could place some pipes in a near-critical zone.
Absolutely critical difference in outcome there.
And we also learned that small variations or uncertainties in material properties like flow stress and fracture toughness are a far greater concern for shifting the safety margin than small variations in physical dimensions like crack size or pipe thickness.
That was a key finding from the sensitivity analysis, yes.
All right.
And that leads us, I think, to a final provocative thought for you, the listener, to consider. The sensitivity analysis demonstrated pretty clearly that flow stress and fracture toughness are the two most variable inputs, potentially causing up to 7% and 10% changes in those final safety ratios, LR and KR, respectively. Now, since these properties are inherent to the weld material itself, and they depend entirely on the material supplied and the specifics of the welding procedure used.
Right, the quality control side.
Exactly. How much tighter do material production standards, material testing protocols, and overall quality assurance need to become in the nuclear industry? How tight do they need to be to guarantee that the assessment point, calculated under real-world variability, never drifts into that narrow critical region near the failure line, regardless of which accepted formula an engineer decides to use? That gap between, say, 10% variability in toughness potentially pushing you towards the line and the need for 100% guaranteed safety.
Yeah.
Well, that gap is where the true engineering challenge really lies.